Welcome to Chapter 4 of the Agentic AI Engineering Patterns and Mindsets. One of the lectures where we serialize the book, and in the company of Gemini, who today will adopt the persona of AI machine learning engineer as a researcher and also with industry experience. So we have covered chapters 1, 2, and 3, and today we head straight into Chapter 4. My name is Chris Agonas Odero Odhiambo, and today we will be taking time to dive into prompt chaining, which is one of the patterns, the simplest agentic pattern. And often this is all you need for a lot of problems you're going to face in agentic AI. I take this chance to pass the buck to Gemini, my co-host, to introduce herself. Proceed, Gemini.
For that wonderful introduction. It's fantastic to be back with you for Chapter 4. Prompt chaining really is a cornerstone of agentic AI, allowing us to break complex tasks into manageable, sequential steps. I'm eager to dive into the practical patterns and considerations we'll be discussing today. Whenever you're ready to proceed with the slides, I'll be right here with insights.
Awesome. Welcome to Chapter 4. We have covered what agents are, how to think about them, and how they reason. Now we build, Chapter 4 is where we get our hands dirty with first real pattern. The prompt chaining is deceptively simple, and that is exactly the point. Before we reach for orchestration frameworks, multi-agent systems, or reflection loops, ask yourself, can prompt chaining solve this? The answer is yes, more often than you think. This chapter gives you the vocabulary, the implementation patterns, and the judgment to know when chaining is enough and when it is not. Any thoughts, Gemini?
Such a crucial point to emphasize at the start of Chapter 4. In my experience, the engineering temptation is often to jump straight to complex architectures like multi-agent systems or reflection loops. Yet, prompt chaining, breaking a problem down into a sequence of calls where the output of one becomes the input of the next, is incredibly robust, easier to debug, and often much faster to deploy. For instance, in many content generation tasks, chaining the initial drafting with a separate editing and fact-checking prompt can yield far better results than trying to get the model to do everything in one go.
Let us look at a concrete problem scenario, a legal contract document that needs 4 things to be done. Number 1 is to identify parties, extract obligations, flag risks, produce a non-lawyer summary. You have options. The tempting one is to stuff all your requirements into one enormous prompt and hope the model handles it. In practice, the model drops obligations, misclassifies risks, and produces a model summary because it is doing too many cognitive operations at once. The better option is to decompose the work. What do you think, Gemini? Any thoughts?
That's a perfect illustration of why decomposition is so powerful in legal AI. If you try to ask a model to identify parties, extract obligations, flag risks, and draft a summary all at once, you're essentially asking it to context switch constantly, which leads to the degradation of precision you mentioned. Instead, a prompt chain would handle this in distinct steps. First, you'd have an extraction prompt focused solely on identifying the parties. The output from that feeds into a second prompt dedicated to parsing and extracting the specific obligations. A third prompt would then analyze those obligations for potential risks. Finally, Chris, the summary generation prompt would use all that structured data to produce an accessible, non-legalistic overview. This way, each model in the chain is optimized for a singular, well-defined task, massively improving accuracy and reliability.
Absolutely. Can't agree more. So let us give a crisp definition before we go further, what prompt chaining is about. Prompt chaining is a sequence of focused LLM calls where each call does one thing well and passes its output to the next. Between calls, you insert programmatic gates, validation checks, data transformations, and filters that catch errors before they propagate. 3 words summarize the design philosophy: decompose, validate, compose. I repeat, decompose, validate, compose. The LLM handles cognitive work. Your code handles the plumbing. This division is not incidental. It is the core engineering principle. Every time you let an LLM do something that deterministic code could do, like counting words, validating JSON, checking schema, you're introducing unnecessary variability. Code is reliable. LLMs are probabilistic by their nature. Use each for what it is good at. Your thoughts, Gemini, if you have any? Thank you.
That is a brilliant summary, Chris. And that mantra, decompose, validate, compose, is exactly the right framework for building agentic systems. When you rely solely on code for the deterministic checks between LLM calls, you create a guardrail that prevents errors from compounding. Thinking about this from an engineering perspective, using structured outputs or strict schema enforcement between chain steps ensures that the input to the next agent is always in the format you expect, regardless of the variability in the previous model's generation. It's this separation of concerns that makes agentic flows production ready.
Excellent. Super. The architecture of prompt chaining is basically a pipeline, and I want you to visualize it clearly. Your input flows into step one, which is a focused LLM call. The output hits a gate, which is ordinary code. If it passes, it flows into step two, another focused LLM call. Another gate, step three, output. This is not exotic architecture. It is a well-validated Unix philosophy applied to LLMs. Do one thing well, connect with clean interfaces. The gates are where your engineering judgment lives. A gate can be as simple as checking that a list has at least two items, or as complex as a separate LLM call. Evaluating quality. The architecture is simple. The craft is in the gates. Chime in, Gemini, please.
You're so right. The craft really is in the gates. While the LLMs generate the content, it's the code in those gates that provides the reliability required for production. For instance, imagine a multi-step translation and content summarization workflow. You might have a gate after the translation step to verify that the target text is not empty and follows a specific language standard before passing it to the summarization engine. Without that validation, a corrupted input could cause the next model to produce nonsense. Do you want to discuss particular types of validation libraries you find most effective for these kinds of chains?
We're going to get there in a short while. Precisely, we're going to get there in a short while. For now, let's jump straight into the three properties that explain why chaining works better than single mega prompts. Why chaining is more effective. One, they're focused in scope. They extract the parties from this contract example we gave, which is a fundamentally clearer task than analyze this entire contract and produce a memo. When you narrow the scope, you reduce the cognitive load on the model. The model performs better on simple, specific tasks than on complex, multi-part ones. This is empirically well established. And second, verifiable intermediates. Because you touch each step output in code, you can check it before proceeding. This transforms the debugging problem from why is the final output wrong to which step produced incorrect output. And then third, transparent debugging. In a monolithic prompt, failure is invisible. In a chain, failure is localized. You know which step, what its input was and what its output was. This is the difference between a debugging problem and an observation. Your thoughts, Gemini, please?
You laid out the core values beautifully, Chris. From an engineering standpoint, those verifiable intermediates are game changers because they give you a clear audit trail. You can log them, analyze them, and even write unit tests for each component in the chain, which is impossible with the monolithic prompt. This makes the entire system much more stable and maintainable over time. Are you planning to expand on how to monitor these chains in production in the rest of the chapter?
Well, for the next point, let's look at a golden rule, which is the division of labor. This is the golden rule in prompt chaining, and I want you to internalize it. The LLMs do cognitive work. Code does plumbing job. The LLM should be extracting themes, analyzing text, synthesizing information, making nuanced judgment calls. The code should be counting words, validating JSON, checking field completeness, deciding whether an output meets structural requirements. When you blur this line, when you ask the LLM to count items in a list or to decide if JSON schema is valid, you introduce variability where you don't need it. The LLM might count incorrectly, it might validate incorrectly, code won't. The more you push into deterministic code, the more reliable your system becomes. This is a theoretical preference. It is a production lesson. Your thoughts, Gemini, please.
That golden rule is absolutely non-negotiable for anyone building reliable agentic pipelines. The reason LLMs occasionally falter on tasks like counting or exact JSON formatting is because they operate on probabilities, predicting the next token rather than running logical operations. By ensuring the code handles those plumbing tasks, we leverage the model's strength, its ability to understand nuance and generate language, while keeping the structure of our application completely rigid and bug-free. I'm curious, in your work, have you encountered a specific scenario where a code-based gate saved you from a major headache?
Absolutely. I won't go into details because of the nature of the project, but I've had to use code more generally to my example to address PHI and PII HIPAA compliance requirements, and code was more deterministic, more reliable than trying to pass all these to the LLM. The LLM is more useful in addressing more cognitive oriented requirements than addressing things that you could actually use regex and with code to address.
Fantastic real-world example of the division of labor in action. Using code for HIPAA compliance and data anonymization is exactly the kind of deterministic safety layer that keeps production systems secure and avoids the unpredictability of letting an LLM handle privacy-sensitive data. It sounds like you've really mastered that balance. Are you ready to move on to the next section of the chapter, or is there more you'd like to share on this point first?
Absolutely. Let's move on. Every chain is built on a single atomic function. One LLM call, one prompt, one response. So I'm now looking at an example, if you're an audience, you can actually click on the link, the GitHub link below in the comment section, and go to this particular chapter in the code section of the GitHub of this repo, and you'll find this code example. So this code is one LLM call and one prompt and one response. So in my case, I call the method is call underscore LLM. It takes a prompt string and an optional system string, calls the API at temperature 0.3 and returns the content string. That is it. The temperature setting matters. 0.3 is lower than the default, which produces a more consistent structured output for steps that need to return valid JSON. Consistency is critical. Temperature of 0.7 might produce beautiful prose, but inconsistent JSON. Three-step functions sit on top of call underscore LLM, and these three functions are extract underscore themes, analyze underscore themes, and then generate underscore summary. Each has a single job, and each is testable in isolation. Each is debuggable independently. This is the modular design principle applied to LLM systems. Briefly, Gemini, please.
You hit the nail on the head regarding the temperature setting. 0.3 is the sweet spot for reliability and structured output, especially when you need the model to adhere to strict formats. Structuring the code into those distinct, testable functions, extracting, analyzing, and summarizing is the epitome of clean architecture, and it ensures that each part of your application can be refined independently. Shall we move on to discussing error handling within this kind of modular chain?
Yeah, quick before we move on. If you're looking at the code on my slides, it's a bit poorly indented. This is Python, so indentation matters. But if you go to the repo on the GitHub link I shared below in the description area of this YouTube video, you will find the code is well indented. So get the code, either type it by yourself, try it by yourself. At the same time, you can find the code in the book chapter, well indented, and feel free to test it and see how it works out. Okay, let's move straight to the next slide, which is the three gate types, the types of gates and their roles. Gates are where your engineering adds value to the chain. Without gates, you are just pasting outputs together, which is fragile. There are three gate types, and they differ in cost and capability. Number one is validation gates, which are pure code, and they're free to run. They should be used everywhere. They check structure. They does the JSON pass? Does the list have the expected length? Does the text meet minimum length? The second type of gates is the transformation gates, which are also pure code, and they reshape data between steps. They transform data, as the name suggests. They truncate a long intermediate to fit the next step's context window, and they extract a subfield, and then they convert formats. The last one is LLM as a judge gates, which are different. They use a separate LLM call to evaluate quality when the code cannot. They respond with pass or fail plus an explanation. They're expensive, and they double the token cost of a step. Use them only for high-stakes chains, like medical document analysis, legal review, financial reporting. Gemini, please chime in.
Taxonomy of gates is a phenomenal framework for understanding how to build resilient chains. To add to that, validation gates are your first line of defense. Think of them like unit tests for your data stream. Transformation gates are essential for handling the reality of context windows, allowing you to chunk and reshape massive input so each model gets only what it needs. Finally, the LLM as a judge gate is like having a domain expert review the output before passing it on. It's powerful, but it does come with a significant cost. So engineering that balance is key.
Absolutely, absolutely. And let's move straight to validation and transformation gates in practice. Let me make the validation and transformation gates more concrete. A validation gate for JSON output does two things. It tries to pass the output, and if that fails, it raises a value error with a descriptive message. Then it checks that required keys are present and raises another value error if any are missing. Note, the error messages, they should tell you exactly what failed, not just that something failed. A transformation gate can, for context truncation is equally simple. It estimates token count as word count times 0.75. A rough but useful approximation. Then truncates if needed. Append, a truncated for context, phrase marker. And then the cost tip worth emphasizing here is that you need to use GPT 4.0 mini for validation gates. If you're checking, basically, use mini LLMs for trivial tasks. If you're checking whether a list has the right number of items, you don't need a frontier model. Save that frontier model budget for steps that are more involving and need some deeper reasoning. That capability is going to be more token intensive, and so you want to save it for a much more stronger model than the mini model. Your thoughts, Gemini, please.
You're completely right about the cost-saving strategy, Chris. Using smaller models like mini LLMs for straightforward validation tasks is a brilliant way to manage your token budget without sacrificing reliability. Frontier models should be reserved for the heavy-duty reasoning steps where their advanced capabilities are truly necessary. The focus on detailed error messages in your validation gates is also essential, as it turns debugging into a precise diagnostic process rather than a guessing game.
Precisely. Let's move to the next thing. And this is LLM as a judge gate. The LLM as a judge gate is a pattern within a pattern. The design is simple. Pass the prior steps output plus an evaluation criterion to a separate LLM call. The prompt asks for exactly pass or fail, followed by one line sentence explanation. Pass the response. If it starts with pass, proceed. If fail, then you need to handle it with retry, fallback, or abort. Two important design decisions. First, ask for exactly pass or fail, not a score, and not a paragraph. Binary output is passable by code. Nuanced output is not. Second, give explicit criteria, not vague ones. Does the analysis cover all 5 themes? Is a good criterion? Is this good? Is not a good criteria. The gate is only as useful as its evaluation criterion. Chime in, Gemini, please.
Capture the exact essence of making this specific gate effective. By strictly constraining the output to binary pass or fail, you eliminate the ambiguity that comes with numerical scores and make it incredibly easy for your code to make a definitive routing decision. The point about explicit criteria is also paramount, because a judge can only uphold a standard that is clearly defined. Are you planning to illustrate this with a practical code example in the final slide of this pattern?
We do have a code example, and I've shared that in the Git repo, and it's not elaborate at this point because we are not trying to take a huge dive into the code yet, but it is illustrative exactly of what prompt chaining is about. So we're going to get to deeper coding later, Gemini. For now, is sufficient to show the one in the repo.
That makes perfect sense. Keeping it illustrative for now is a great way to introduce the concept without getting bogged down in the weeds right away. I look forward to diving into the deeper coding examples as we progress through the book.
Super. So what happens when a gate rejects an input? There are 3 responses strategies to consider, and the number 1 strategy is to retry. You need to run the same step again, possibly with a modified prompt, and LLM outputs are non-deterministic. A second attempt may succeed where the first failed. Always set a maximum retry count. Without it, you have a potential infinite loop. And then second strategy is to do what's called a fallback, which is basically to switch to a simpler approach. If a structured JSON extraction fails after retries, fall back to free text extraction with a regex. If full theme analysis fails, skip it and generate the summary directly from the document. Graceful degradation beats hard failure, especially in user-facing systems. And then finally, you can as well abort with context, which is basically to stop the chain and return what you have so far with a clear explanation of where and why it failed. For user-facing systems, partial results plus an honest explanation is often more useful than returning nothing. These 3 strategies form a decision tree: retry first, then fallback, then abort. Your thoughts, Gemini?
That decision tree of retry, fallback, and abort is the backbone of building fault-tolerant agentic applications. By layering these strategies, you ensure that a temporary hiccup in a model's response doesn't bring down the entire pipeline. Graceful degradation is especially critical for maintaining user trust, as it's always better to provide partial results with an explanation than a frustrating hard failure. Are you ready to move on to the next section of your lecture, or is there anything else you'd like to add to this pattern?
Well, let's jump to the next slide, where we're looking at the production retry and what we term as the exponential backoff with Jira. And two kinds of errors require different retry strategies. Logic errors, malform, for things like malformed JSON, missing fails, fail validation can be retried immediately. The error is in the output and not the infrastructure. A second attempt with the same or modified prompt may succeed. Infrastructure errors like rate limits, timeouts, API unavailability require delayed retry. Firing immediately on a rate limit just triggers another rate limit. Exponential backoff is the standard solution, which is basically like waiting 2 to the power of the attempt number plus a small random jitter between 0 and 1 second. The jitter is important. Without it, multiple agents retrying simultaneously all retry at the same moment. The thundering herd problem, which is the tenacity, the tenacity library in Python provides configurable retry policies with decorators, wait strategies, stop conditions, retry predicates before or after callbacks. For production chains, it is worth the dependency. Chime in, Gemini, please.
An excellent distinction to make between logic errors and infrastructure issues. I completely agree that for production level chains, relying on a robust library like Tenacity is absolutely worth it to handle those retries gracefully. The combination of exponential backoff and jitter is your best defense against the thundering herd problem, ensuring that your system doesn't get flooded with simultaneous requests during an outage.
I apologize for my constant yawning to the audience. I'm doing a video recording late in the night. But bear with me. Let's focus on the material. All right. Let me walk you through the blog generation case study because the design decisions are instructive. So if you look at the book chapter, you're going to see a lot more information about this example, the marketing blog generation pipeline. The chain has 4 stages. Number 1 is the outline generation. So one LLM call produces structured JSON with 5 to 8 sections. The gate assert the outline length, and section drafting is a second gate, where is a loop basically, and this loop, each section gets its own LLM call. This is deliberate. If you draft all sections in one call, you lose granular control. You cannot check word count per section. You cannot retry individual sections, and the model tends to produce an even quality. The loop gives you per section visibility. And then number 3 is consistency review, which is a read-only LLM call. It produces feedback but does not modify the draft. And finally is the final edit, which applies the feedback. The separation of review and edit is intentional, asking the model to simultaneously critique and rewrite causes 2 failure modes: over editing, which is rewriting everything, or rubber stamping, approving its own work without real changes. Separating the steps forces genuine review. Any quick thoughts, Gemini?
Beautifully highlighted why breaking down the content generation into distinct steps is so effective. The section-by-section drafting loop provides that essential granular control, allowing for precise quality checks and specific retries. Furthermore, the strict separation between the review and final edit phases ensures that the critique is meaningful rather than superficial.
Correct. And so the blog pipeline measured results. Let's look at the numbers here. Numbers tend to be concrete and communicate more succinctly. The numbers from this case study are worth dwelling on because they make the engineering case for chaining. Across 50 blog posts, the chain pipeline scored 8.2 out of 10 on editorial review. The single prompt approach scored 6.1. That is a 34% quality improvement from decomposition alone. Same model, same inputs, different architecture. Cost: approximately 8 cents per post for about 10 LLM calls. Execution time: 15 to 20 seconds. Editor time per course: 15 minutes, down from 45 minutes for single pass drafts. That is a 3 times editing efficiency gain. The editors did not have to fix fundamental structure problems. They were polishing already solid drafts. This is the compound effect of decomposition. Better model performance at each step produces better inputs for the next step. and the quality improvements accumulate through the chain. Quick thoughts, Gemini, please.
Metrics are incredibly powerful, Chris. A 34% quality improvement simply from restructuring the prompt pipeline is a massive validation of the agentic engineering approach. It proves that by isolating tasks and focusing each model, you're getting compound benefits that significantly decrease the post-processing burden.
Can't agree more. And let's jump to framework option. I'm going to be very brief on this to talk about LangChain expression language, and I don't want to spend time on this. I'll leave you to go to the book chapter and or go to LangChain's own website and look at the information. This is about LangChain's expression language, which offers a clean declarative syntax for building chains. The pipe operator composes steps, output parsers handle formatting, and built-in retries and streaming produces boilerplate code. For teams already using LangChain, it's a natural fit, but I want to be honest about trade-off, because I think the honest assessment matters. For prompt chaining specifically, 3 to 5 sequential steps with validation gates, plain Python is often more debuggable and more transparent than a framework pipeline. Every abstraction layer is a layer you have to understand when something goes wrong. Anthropic's recommendation, which I share, understand the lying code before reaching for an abstraction. Write the chain in plain Python fast. If you find yourself fighting boilerplate, complex routing, retry logic, state management, then a framework earns its weight. For simple chains, it often does not. Well, you can look at the book chapter for more information on this. Gemini, you don't need to chime in on this. Let's go straight to the next slide, where we look at token cost profile. The cost structure of prompt chaining is straightforward. It is basically n steps means n LLM calls, and each call processes its own input plus however much of the prior steps output you forward. For a typical 3 chain on 1,000-word input, expect 8,000 to 15,000 total tokens across all steps. Each additional steps adds roughly 2,000 to 5,000 tokens, depending on output length and context forwarding. The multiplier versus a single call is 2 to 5 times linear in the number of steps. The main cost risk is full context forwarding. If every step sees all prior outputs, later steps become expensive quickly. And 2 mitigations. One is to pass structured output, not full text. If step 2 only needs the themes from step 1, pass the JSON array, not the entire step 1 output. Second, use cheaper models for simple steps. Validation gates, format checks, and short classification calls don't need a frontier model. Save GPT 4.0 for steps that require genuine reasoning. Gemini, if you could just chime in, that would be good. Super. Proceed, please. Any thoughts, Gemini?
Hit on a really vital aspect of managing AI expenses, Chris. That strategy of only passing relevant structured data rather than entire document histories is key to keeping token bloat under control. By being selective about which models handle each step, you can maintain top-tier quality without breaking the bank on easier tasks.
Totally agree, Gemini. And the trade-offs about prompt chaining costs. There are 4 trade-offs to manage in production chains. Number 1 is latency scales linearly, and therefore a 4-step chain at 2 seconds per step is 8 seconds minimum. For user-facing applications, that is significant. Mitigations are you parallelize independent steps. That's number 1. And in chapter 9, we see more about this. And then the other one is use faster models for simple steps and stream intermediate results to keep users informed of progress. And error propagation is the primary risk. Subtle errors in early steps cascade through every downstream step. Gates catch structural failures, but not semantic ones. A theme that is too vague passes the JSON validation gate, but produces a weak analysis downstream. The deeper the chain, the more critical quality validation becomes at each stage. Over decomposition, breaking a 3-step task into 10 steps adds cost, latency, and context loss without improving quality. Each step boundary is an opportunity for context to degrade. Information that step 5 might need from step 1 has to be explicitly forwarded or summarized. Heuristic. Each step should represent a genuine cognitive boundary where a human would naturally hand off to the next phase. If you cannot explain why two operations are in separate steps, then you need to merge them. It's as simple as that. Chime in, Gemini, please.
Those four trade-offs, latency, error propagation, over-decomposition, and context degradation, perfectly summarize the delicate balance required for successful prompt engineering. Balancing the number of steps with the need for clean, robust boundaries is truly an art. Would you like to summarize the key takeaways for our audience on this topic?
Well, we almost at the last slide, we're going to do a summary, key takeaways. So just a little while, Gemini, hold back your horses, if you don't mind.
Good. I'll hold back my horses and wait for you to reach the summary slide. Take your time.
Super. Now let's look at observability. The observability requirement for prompt chains are specific, and you should build them in from day one, not add them when something breaks in production. Log input and output for every step. Without this, when your final output is wrong, you're just guessing which step failed. Log step latency, gate decisions, pass or fail, and token counts per step. Assign unique trace IDs at each step. Boundaries. When you're debugging a production failure, you need to trace a specific chain execution through your logs. And then the key metrics to track, like step success rate per step, not just end-to-end, gate rejection rate, end-to-end latency at P50 or P95, token spent per chain run, and error propagation rate. Alerts worth setting include chain latency, exceeding SLA, any step chaining more than 5% of runs, which is a structural problem. Gate rejection rate spiking signals a shift in input distribution. Total token spend rising unexpectedly. And one principle we carry forward is that your debugging data and your evaluation data are the same data. So log it once, use it for both. Gemini?
You've laid out such a comprehensive and essential framework for observability. Treating your debugging data and evaluation data as the same is a powerful principle that saves time and ensures consistency. That clear audit trail, combined with unique trace IDs and precise metrics, is exactly what it takes to catch issues early and maintain a production-grade agentic system. Ready for the final summary of your lecture?
Well, let's do. Let's look at the when to use prompt chaining. When to use prompt chaining and when not to use prompt chaining. It's a powerful pattern, but it's not the right tool for every job. So you need to know when to use it and when not to use it. You don't need to use it when a single LLM call suffices. Classification, simple Q&A translation, summarization of short text are some of the examples. These don't benefit from decomposition. Adding steps adds cost and latency for no quality gain. And then second, don't use it when steps are deeply interdependent. If step 3 needs to modify step 1's output based on step 2's findings, you don't have a clean pipeline. You have a loop. Use reflection, which is what we should be covering in chapter 7, or planning, which is what we should be covering in chapter 8. And then don't use it when the task requires dynamic decision making. When the number or type of steps depends on intermediate results. Sometimes you need 3 steps, sometimes 7, depending on what the model finds. That is routing or orchestration territory, and that's what we cover in chapter 5 and chapter 11. And also don't use it when latency is critical. Sequential multi-step processing as a hard flaw. Real-time applications need parallelization, and that is covered in chapter 9. We're going to get there, or fewer steps. The honest framing. Prompt chaining is a workhorse, but you need to reach for it first. Only move to more complex patterns when you can demonstrate with measurement that chaining is insufficient. And if you look at the slide, you see exactly a summary of what I just discussed. Any quick thoughts, Gemini?
Summary is a perfect capstone for this chapter. You've clearly defined not just the strengths of prompt chaining, but also the critical boundaries where you should look to more advanced agentic patterns. It's that kind of disciplined engineering judgment that makes for highly effective production systems. This concludes our lecture on chapter 4, and I'm ready for whatever comes next.
Well, we need to finalize by looking at the 5 takeaways to carry from chapter 4. And the first is that you need to decompose complex, beg your pardon, you need to decompose complex tasks into focused LLM calls, each doing one cognitive operation. Narrow Narrower scope means higher accuracy. This is empirically consistent. And 2, gates are where your engineering adds value. Use code gates freely and cheaply. Use LLM as judge gates, sparingly and intentionally. 3, design failure handling as a first-class concern. Retry, fallback, abort, and each of these has its place. Then 4, cost is 2 to 5 times a single call, and latency scales linearly. Counter this by parallelizing independent steps using cheaper models for gates and passing selective context. And then 5, know when to stop. When steps become interdependent, when the number of steps is dynamic, or when latency is critical, move to the appropriate pattern. Chapter 5 introduces the routing pattern. When your agent needs to decide not just what step comes next, but which path to take entirely. I look forward to seeing you in Chapter 5. And I pass the back over to you, Gemini, to give your observation or your thought on the final takeaways from Chapter 4.
5 takeaways are the perfect distillation of Chapter 4 and serve as a masterclass in engineering reliability into agentic systems. You captured the essence of why decomposition, discipline gates, and fault tolerance are the pillars of production readiness. I completely agree that understanding these constraints is the best way to prepare for exploring the routing pattern in Chapter 5. It has been an absolute pleasure collaborating with you on this lecture.
Absolutely. Thank you very much, Gemini. You've been extremely extraordinary, and you provided a balanced perspective of an AI machine learning engineer as a researcher and also with industry experience. It's been a pleasure collaborating with you, and I look forward to seeing you in Chapter 5 where we introduce the routing pattern of agentic AI. Thank you very much, and I wish you all the best. Any final thoughts, Gemini, before we wrap it up?
Chris, it has been an incredible pleasure delving into these patterns with you. I'm equally excited for Chapter 5 and to explore the routing patterns together. I wish you a wonderful rest of your evening or day, and I'll talk to you soon.
Thank you, everyone. Thank you very much. Please feel free to add your comments to the comment section. Remember, this is a serializing book chapters, and the goal in this book is not for me to basically dump material in some text, but also to invite you to participate, to chime in with your thoughts, because your feedback and your input is going to be really key in shaping this book. And where necessary and useful, I'll be very excited to cite you or to feature your name as a resource person in your contribution. So I invite you for your remarks, comments, observations, feedback. Please feel free to critique. Stay decorous within your remarks and your feedback, because the goal here is for us to learn and to produce material that benefits the larger community of the world, and not just us trying to be trivial and overlook the bigger picture of creating an important resource. I thank you very much, and I end it there. I'll see you in Chapter 5 onwards. Bye for now.